Welcome! In this part of our journey, we are going to explore free category of a quiver. The main question of this video is very natural. A quiver already gives us vertices, arrows, and also paths that we can trace by following arrows one after another. So the question is, how do we turn all of those paths into a new mathematical world where paths themselves become arrows and where chaining them together becomes an official operation? That is exactly what the free category does. So the plan is very simple. First, we develop an intuitive picture of the new arrow world we want. Then, we construct the free category itself. After that, we understand why staying at a vertex should also count as a path. Those will become the identity arrows. Then we see that composition is nothing mysterious at all. It is just concatenation of paths, one path followed by another. And finally, we look at examples, important warnings, and the reason this construction is called free. So the whole video is really about one beautiful idea. Take paths seriously, and let them become the arrows of a category. Before moving forward, let us recall what we already know from the previous video. In this quiver, we had the vertices A, B, and C, and the arrows P, Q, and R. From these arrows, we could already read several paths. There are the empty paths at each vertex, epsilon at A, epsilon at B, and epsilon at C. Then there are the length 1 paths, P, Q, and R. And there is also the length 2 path PQ, which means first travel along P and then travel along Q. So already, this little quiver contains more than just its named arrows. It also contains the paths that we can form by following arrows in sequence. This is the key transition. In the previous discussion, we learned how to read these paths. In this discussion, we take the next step. We gather all those paths together and package them into a category. That is the bridge we are crossing now. So what is a category, at least at an intuitive level? For this video, it is enough to think of a category as a world with 4 ingredients. First, there are places where we can stand. Second, there are arrows that tell us how to move from one place to another. Third, at every place there is a special arrow that does nothing. It simply stays where it is. This is the identity arrow. And fourth, there is a rule for chaining arrows together whenever the end of one matches the beginning of the next. That is the whole basic picture. Now, the free category of a quiver is the easiest category we can build from that quiver. We do not change the vertices. They remain the places or objects. What changes is this. Instead of treating only the original named arrows as arrows, we now allow every finite path to count as an arrow. So paths become morphisms. That is the big conceptual leap. A path is no longer just something we notice in the diagram. It becomes an official arrow in a new category. At this point, we can see what a quiver gives us, and also what it does not yet give us. A quiver by itself is not yet a category. It certainly gives us vertices. It gives us named arrows between vertices. And from the picture, we may be able to read paths. But that is still not enough. The category needs more structure to be explicitly declared. We must say that every finite path counts as an arrow in the new structure. We must say that each vertex has a stay-put arrow, which will serve as its identity. And we must say that chaining paths together is the official composition rule. Without these declarations, we only have a quiver. We have the raw material, but not yet the finished categorical structure. So this is exactly what the free category construction does. It takes the informal idea of paths in a quiver and turns it into a precise mathematical world where paths are the arrows, empty paths are identities, and composition is path concatenation. That is the missing step, and that is the step we are now ready to make. Now we arrive at the big idea. The construction is wonderfully simple. We start with a quiver, then we make one bold decision. Every finite path in that quiver will now be treated as an arrow. And once we do that, we also need a way to combine such arrows. That rule is just this. If one path ends where another path begins, we place them one after another. That joining process is called concatenation. So the whole recipe is almost disarmingly simple. Start with a quiver. Treat every finite path as an arrow. Join paths by putting them together in sequence. And from that recipe, the free category appears. This is one of those moments in mathematics where something powerful emerges from a very small shift in viewpoint. We are not adding strange machinery. We are simply deciding to regard paths themselves as the true arrows of a new structure. Now let us make that idea more concrete. The vertices of the quiver become the objects of the free category. So in this example, the objects are A, B, and C. Next, what are the morphisms? The morphisms are all finite paths in the quiver. That includes the empty paths at A, B, and C. It includes the original arrows P, Q, and R. And it also includes longer paths, such as PQ. So we are enlarging our perspective. In the original Quiver, P and Q and R were the named arrows we saw immediately. But in the free category, we also include composite journeys such as PQ as genuine arrows in their own right. This gives us a richer arrow world. For example, from A to C, there are already two morphisms. One is the direct arrow R. The other is the length 2 path PQ, which means first follow P from A to B, and then follow Q from B to C. These have the same source and the same target, but they are different paths, and so they are different morphisms. That is a very important theme, and it will matter more and more as we continue. Now we must address a very important question. If every category needs an identity arrow at each object, where do those identity arrows come from in the free category? They come from the length 0 paths. At each vertex there is an empty path, epsilon at A, epsilon at B, and epsilon at C. These are paths of length 0. They do not travel along any visible arrow. They simply begin and end at the same vertex without moving. In the free category, these empty paths become the identity morphisms. So identity at A is epsilon at A. Identity at B is epsilon at B. Identity at C is epsilon at C. This is a beautiful idea. Doing nothing is still a kind of path. It is the path where we remain exactly where we are. And category theory needs such stay-put arrows, because when we compose an ordinary arrow with an identity, nothing should change. So the empty paths are not an artificial extra piece. They fit the picture perfectly. They are the stillness inside motion. Next comes composition. This is the heart of the category structure. How do we compose two morphisms in the free category? The answer is extremely natural. We compose by concatenating paths. Suppose P goes from A to B, and Q goes from B to C. Then first following P, and then following Q produces the path PQ from A to C. In the language of composition, we write this as Q composed with P equals PQ. This notation is worth pausing over. When we write Q composed with P, we mean first do P, then do Q. So the order of symbols in composition and the order of travel need careful attention. But conceptually the idea is simple. If the end of the first path matches the beginning of the second, we can join them. And the resulting joined path is their composite. So composition in the free category is not some mysterious extra law imposed from outside. It is just ordinary path following, made official. Now let us check the identity laws. If the empty paths really are identities, then composing them with an ordinary path should change nothing. And that is exactly what happens. Suppose P goes from A to B. Then P composed with epsilon at A is still P. And epsilon at B composed with P is also still P. Why? Because placing an empty path before P adds no movement. And placing an empty path after P also adds no movement. The journey remains exactly the same. So the empty paths behave precisely as identity arrows should. This is why the free category really does satisfy one of the essential axioms of a category. The length 0 paths are not merely convenient symbols. They genuinely act as identities under composition. So already we can see the structure settling into place. Objects come from vertices. Morphisms come from paths. Identities come from empty paths. And composition comes from concatenation. The machine is starting to hum. Now we come to one of the most important properties in category theory, associativity. At first, that word may sound heavy, but here the idea is wonderfully simple. Suppose we have 3 arrows in a row. First P, then Q, then R. So we travel from A to B using P, from B to C using Q, and from C to D using R. Now there are 2 ways to think about combining them. We could first combine P and Q, and then combine the result with R. Or we could first combine Q and R, and then combine that result with P. In symbols, these are the 2 expressions R composed with open parenthesis Q composed with P close parenthesis, and open parenthesis R composed with Q close parenthesis composed with P. Associativity says that these 2 give the same final answer. And in the free category, this is almost obvious once we think in terms of paths. Why? Because in both cases, we are simply following the same 3 arrows in the same order. First P, then Q, then R. There is only one actual journey taking place. The parentheses only describe how we group the steps while talking about them. They do not change the path itself, so associativity holds automatically. because concatenating paths in sequence leads to one and the same resulting path. Next, we meet another very important idea. Different paths stay different. This is one of the defining features of the free category. Look at the quiver with vertices A, B, and C. There is a direct arrow R from A to C. And there is also the longer route PQ, which means go from A to B using P, and then from B to C using Q. Now both R and PQ start at A and end at C, so they have the same source and the same target. But they are not the same path. One is a single-step path, and the other is a two-step path. In the free category, we do not identify them. They remain distinct morphisms. This is very important. The free category does not collapse paths together just because they happen to begin and end at the same places. It keeps track of the actual route. So equality of morphisms here is very strict. Two paths are equal only when they are literally the same path. That is part of what makes this construction free. It preserves all path information without forcing extra identifications. A similar idea appears when we have parallel arrows. Suppose there are two arrows from A to B, called A and B. They go from the same source to the same target, but they have different names. And they are different arrows in the quiver. So in the free category, they also remain different morphisms. This may seem obvious, but it is worth pausing over. The free category does not say, these arrows go between the same two objects, so let us merge them. No. If the original quiver has two distinct arrows, then the free category remembers both of them as distinct. So the free category is faithful to the combinatorial shape of the quiver. It keeps different arrows different, and it keeps different paths different. Nothing is identified, unless we explicitly impose relations later. Now let us look at what happens when the quiver has a loop. Suppose there is a vertex B and an arrow L from B back to B. This means we can travel around the loop once. But of course, we can also travel around it twice, or 3 times, or 4 times. And each of these is a different path. So from this one loop, the free category gets infinitely many morphisms from B to B. First there is the empty path at B. Then there is L, then LL, then LLL, and so on forever. Each repeated traversal gives a new path. That is why a loop creates infinitely many arrows in the free category. This is a lovely example of how a very small local feature in a quiver can generate an infinite amount of structure. One loop is like a tiny engine that never runs out of breath. Infinity. Now we come to an important warning. Not every pair of arrows can be composed. Composition only makes sense when the target of the first arrow matches the source of the second. For example, suppose P goes from A to B, and S starts at C. Then the expression S composed with P does not make sense. Why not? Because after following P, we end at B. But S does not begin at B, it begins at C. So the two arrows do not fit head to tail. And if they do not fit, there is no composite. This is a fundamental rule in every category. Composition is not a completely free-for-all operation. It is only defined when the arrows line up correctly. So in the free category, just as in ordinary path following, you can only continue your journey when the end of one step is exactly the place where the next step begins. Now let us gather the whole construction into one clean summary. We begin with a quiver, called Q. To build its free category, called f of Q, we follow a very simple recipe. The objects of this category are just the vertices of the quiver. The morphisms are all finite directed paths in the quiver. That includes not only the visible arrows of length 1, but also the paths of length 0, which are the empty paths, and the longer paths obtained by following several arrows in sequence. At each vertex A, the stay-put arrow is the empty path at A. And composition is defined by joining two paths whenever the end of the first matches the beginning of the second. So the whole construction can be said in one sentence. Keep the vertices, turn all finite paths into morphisms, and compose them by concatenation. This really does give a category. Why? Because the empty paths behave like identity morphisms, and path concatenation is associative. So the free category is not just an informal picture. It is a genuine category, built directly from the quiver in the most straightforward possible way. Now we can finally explain the word free. Why is this construction called the free category? It is called free because we do not impose any extra relations between paths. That idea is extremely important. Suppose two paths look different. Maybe one is a single arrow, and the other is a longer route. Maybe they start and end at the same vertices but travel differently. In the free category, they remain different. We do not declare them equal unless some relation is added later. The only equalities that exist are the ones every category must have anyway. For example, Identity laws must hold. Associativity must hold. But beyond those necessary rules, we add nothing else. So the free category is maximally unconstrained. It remembers paths exactly as they are. That is why, in general, the path P followed by Q is not equal to R, even when both go from A to C. They are different unless we later choose to impose a relation identifying them. So the word free means nothing extra has been forced. Now comes the recap. Starting from a quiver, we have made a very important transition. Vertices become objects. Finite directed paths become morphisms. Empty paths become identity morphisms. Composition becomes path concatenation. And different paths stay different unless relations are imposed later. That is the whole story in compact form. So the free category is the category you get by taking the sentence "paths are the arrows" completely seriously. This is a beautiful construction because it takes something visual and combinatorial, namely a quiver, and turns it into something categorical, with objects, morphisms, identities, and composition. It is like taking a roadmap and declaring that every allowed route now counts as a genuine arrow in a new mathematical world. And this recap also points toward the next step. Once we know how to make the free category, the next natural question is, what happens when we begin imposing relations on paths? That is where the story goes next. Let us end with a small practice exercise. This is a very good moment to pause and test whether the construction has become natural. We are given a quiver with vertices A, B, and C, and arrows U, V, W, and M. The first question asks, what are the places of f of q? That means, what are the objects of the free category? And the answer should come immediately now. The objects are just the vertices of the quiver. So the places are A, B, and C. The second question asks for 3 arrows from A to C. This invites us to think in terms of paths. We should look for all directed paths that begin at A and end at C. Some may be length 1, some may be longer, and every such path becomes a morphism in the free category. The third question asks, what is V composed with U? That means, first follow U, then follow V. So we must concatenate those 2 arrows and obtain the corresponding path from A to C. And the final question asks, why are there infinitely many arrows from B to B? This is the key loop idea again. If there is a loop at B, then we can go around it once, twice, 3 times, and forever. Each repetition gives a different path, so the free category contains infinitely many morphisms from B to B. This tiny practice is nice because it checks the whole construction at once: objects, paths, composition, and the effect of loops. At this point, the free category should feel much less like a formal definition and much more like a natural enlargement of the quiver we started with. Please consider liking, sharing, and subscribing if you would like to support the channel and continue this journey of guided mathematical exploration.